Hello, my name is Sarnath Kannan, and in this video I am going to talk about the kernel trick. If you are a data scientist, you probably already have heard this term called kernel trick or kernel function somewhere, but most likely you don't understand it deep enough. And that's fine, because I was in the same state as you, but then I started investing time on watching videos, reading books, reading articles, and I still don't understand it fully, but I understand it somewhat better. And I'm going to condense and present my understanding in a user-friendly way. And why I say user-friendly is that I've read all these resources. I find that this particular topic is not presented in a user-friendly way in many of the resources, which is very sad. So in this video, I'm going to fix that problem, and I'm going to present this in a very user-friendly way. And after watching this video, you'll be able to understand kernel functions in a deeper way. And if you watch this video and then go and read some resources on kernel functions, you will be able to understand them much better. Okay, that's my guarantee. So this video is organized like this. I will first talk about linear classifiers, then nonlinear classifiers, problems associated with nonlinearity, how kernel functions solve these challenges, and finally the theoretical underpinnings of kernel functions. By theoretical underpinnings, what I mean is, it is said that kernel functions are equivalent to dot products arising from high dimensional space. So what is this high dimensional space? What is the proof for this? All this we will discuss and more. Let's jump into the video. Before I delve into the video, I want to register my sincere thanks and acknowledgements to Martin Trenchany, who is my manager, for his thoughtful and patient review comments on this video. I have listed his LinkedIn profile here. Also, Martin hails from Hungary and he writes on a variety of topics. You can check www.bytepond.com to read some of his thoughtful blogs. Thank you, Martin. If you're new to classification, here is a quick-fire introduction. You see a table here on your right. It has 3 columns in it. It captures the height of a person, weight of a person, and also information whether a person is a child or adult. Now, with this data, if I get a new data point, a height and weight of a person, I should be able to classify whether the person is an adult or not. So that is the problem we have. And since this decision is based on the data that we already have, this is called as data-driven decision making, and the process by which we do this is called as machine learning. And how do we do that? We take these data points and then we cast it in a 2-dimensional space. The x-axis is height, y-axis is weight, and the color of the data point is whether the person is an adult or child. The blue ones are the adults, the green ones are the children. Now the data science algorithm finds out this red line that separates the green and blue. Once this red line is found out, if I get a new data point, I can easily say whether it is falling on the right side or on the left side. Based on that, I'll be able to classify a new data point as a child or an adult. This process is called as classification. And since we learn a straight line, this is a linear classifier. Here is a linear classifier called as max margin classifier. The specialty of this classifier is that it maximizes the distance between the decision boundary and certain data points called as support vectors. Support vectors are those data points which are closest to the decision boundary. In the video, you can see that certain data points are marked as SV. Those are the support vectors, and this type of classifier maximizes the distance between those support vectors and the decision boundary. This is one type of linear classifier. That's all. In this example, we have added a new column called IQ. So we have got height, weight, and IQ, and using that we classify whether a person is an adult or child. So we throw this data at a data science algorithm, and it comes up with a classification boundary, which is a plane in 3 dimensions that separates the blue and red points. So if you see that the classification boundary is a linear function of its features. So that is why these kind of classifiers are called as linear classifiers. But should this work in all cases? Perhaps not. For example, as people age, right, their IQ level starts dropping. So you will not have a clear boundary between the blue and red points. In those cases, we may need something more, a nonlinear classifier. Before we go into nonlinear surfaces, we will first take a simple 1-dimensional example of classification, which is linear. Then we will slightly complicate the problem and make it nonlinear. Okay, so first to the simple linear problem. So we have a 1-dimensional surface, and you have got blue points to the right of 5 and green points to the left of phi. So if you're given a new point, a new x value, all you have to do is subtract phi from that, calculate x minus phi. If it is greater than 0, then it is blue. If it is less than 0, then it is green. Now let us complicate this problem a bit. In the new setup, the blue points are sandwiched between the green points, and the blue points lie between 2 and 7 with green points on either side. So in such a case, if you're given a new point x, how will you determine that point as blue or green? What mathematical operation would you run on x? Will it be a linear operation or will it be a non-linear operation? What will be your guess? Pause this video, make a guess, and wait for the next slide. Congrats on getting this right. If you multiply x minus 2 with x minus 7, and if the result is greater than 0, then it's a green point. If it is less than 0, then it's a blue point. So the discriminant in our case is x squared minus 9x plus 14, which is the expansion of x minus 2 multiplied by x minus 7. So this is clearly a quadratic decision function. It's a non-linear quadratic decision function. On a related note, I found this interesting 1D example in some university's tutorial, but I totally forgot which university it was, so I'm unable to give credits for them. So if any of you know which university it is, please let me know. I'll include the link in the description. Thank you. Look at the expression x squared minus 9x plus 14. If I substitute x squared with y, I get y minus 9x plus 14, which is a linear combination of y and x. And if I equate that to 0, I get the equation of a straight line. Armed with this perspective, I take all my points, my one-dimensional points, and try to plot them in 2 dimensions. Now, how can I plot in 2 dimensions? I don't have a y coordinate. I have only one coordinate, x. So for the y coordinate, I just simply use the square of the x coordinate. So x comma x squared. So if your x coordinate is 5, I plot that point at 5 comma 25. If the x coordinate is 2, I plot the point at 2 comma 4, and so on. So once I plot these points, my green and blue points on the 2D plane, and if I can run a linear classifier which can classify the green and blue points correctly in 2D plane, I will get a linear decision boundary, which is like y minus 9x plus 14 equal to 0. But I know that my y coordinate is square of x. So if you substitute the higher coordinate y with the lower coordinate equivalent, which is x squared, you get x squared minus 9x plus 14 equal to 0. So the decision boundary is linear in 2 dimensions, but non-linear in 1 dimension. Correct? This is the single most important takeaway from this slide. What this means is that we don't have to do a lot of stuff to get non-linear classifiers. All we need to do is to take our points, project it to a higher dimension, and develop a linear classifier in that dimension, and that would automatically correspond to a non-linear decision surface in the lower dimension. As simple as that. Just like how we saw we could promote a one-dimensional point to 2-dimensional space, we could do the same to a 2-dimensional point. Just pick up a 2-dimensional point x comma y, we can project it to 3D space and call it x comma y comma z or z, where z or z is equal to a function of x and y. So in the figure that you're seeing, I have used a complex polynomial function of x and y to arrive at z or z. So once you are in this new space, 3D space, all your points are now projected in 3D space. Now you can develop a linear classifier whose decision boundary looks like a linear combination of x, y, z or z is equal to 0. Now if you substitute back your z or z with a complex polynomial function of x and y, then it becomes a very complex function which gets equated to 0. That will be your decision boundary. And the roots of that equation will form the decision boundary in your 2D plane. And that would be a extremely nonlinear decision surface. And that is exactly how we build a complex decision surface on 2 dimensions. Now, should we always project a 2-dimensional point to 3 dimensions? No. We can project it to 4, we can project it to 5, you can project it to 10. It's totally up to you. For example, you can take x comma y, and then we can say x comma y comma x squared comma y squared. That's a 4-dimensional point. We can map an x comma y to x comma y comma x squared comma y squared comma xy. That's a 5-dimensional point. Now we can go to higher order powers, x cube, y cube, x power 4, y power 4, x power 4 into y power 4. It can go on like that. As you increase the order, the number of polynomial terms that you could get is practically limitless. So that is another subject of complexity that we need to deal with. But it's clear that we can take a low dimensional point, project it to a high dimensional point, build a linear classifier in high dimensional space, and that will correspond to a complex nonlinear surface in your lower dimensional space. Okay, what you see here is a complex equation that I have plotted using Grapher. So you see this colorful plane in the middle, that is the xy plane. For each one of the xy points, I compute a complex function of f of x comma y and call it as z or z. So I convert a 2D point to a 3D point, basically a higher dimensional point. So the complex curve that you see here, that is the plot of x comma y in x comma y comma z plane, where z is a complex function of x and y. Now, if I have a set of points to classify on the colorful plane in the xy axis, now I can map it to this complex curve. I can map each one of those points to the complex curve, and then I can develop this classifier that you see here. Right? You see the classifier? That is a classifier plane. So let's say that if I learn this classifier plane, then the classifier plane's equation says it's ax plus by plus cz is equal to some constant, and then we can replace the z by function of x comma y. So this becomes a complex function of x comma y equal to constant, which corresponds to a nonlinear decision boundary in xy plane. So this is the idea of using higher dimensional mapping to achieve nonlinearity at a lower dimensional space. So let us take a look at second order high dimensional spaces. If our input data point was two dimensional, which means that our points had x comma y coordinate, and we want to use higher order, which is second order features, then we can go until 5 dimensions: x, y, x squared, y squared, x multiplied by y. So we get 5 dimensions. If our input feature space had 3 dimensions, we can go until 9 dimensions in second order high dimensional space. Similarly, generally, if we have n dimensions in our input data point, then we can go until n into n plus 3 divided by 2 number of dimensions. Now it's very clear that the number of dimensions is quadratically exploding, right? So that is the takeaway from this slide. Let's look at third order high dimensional space. If your input data point was n dimensional, and if you want to project it into a third order high dimensional space, we could go until n into n squared plus 6n plus 11 divided by 6. This is the order of n cube. So the number of dimensions you could have in third order high dimensional space is literally the cube of your input dimensions. Previously we saw quadratic for second order. For third order it is cubic. So just to get some numbers so we get a better idea, if your input data point was 200 dimensional, and if you wanted to project it to a second order high dimensional space that includes all the second order features, your 200 dimensional data point would become a 20,000 dimensional data point. Similarly, if you wish to use all the third order features, your 200 dimensional data point would become a 1 million dimensional data point. And if you want to go to fourth order and fifth order, you will be talking about millions and billions of dimensions. So this makes the high dimensional space projection an extremely costly affair. This mapping of points to high dimensional spaces comes with its own set of problems. One is a computational issue, another is a conceptual issue. The conceptual issue is that when you project your points to such high dimensional spaces, there could be several hyperplanes which could clearly classify your data points. Now, which one of these hyperplanes is optimal? Which one of them generalizes very well? This issue fortunately has been solved, and it has been found that the max margin classifier is the most optimal hyperplane that we can build in high dimensional spaces, and it also generalizes very well. So the conceptual issue is out of our purview. The second issue is the computational issue. The computational issue is that when each one of your data point has million dimensions, even to perform a dot product between two data points, you have to perform million multiplications and million additions. So this is a huge stress on your compute resources, and Kernel Trick solves this issue, and how it solves it, we will find out. There are several disadvantages to the manual specification of the high dimensional mapping phi of x. We mostly think of polynomial features, but then we don't know what is the order that we should use. Should we use second order? Should we use third order? Should we use fourth order? Which one is relevant to our problem? And this involves significant computational complexity as well. and there's no structure or framework that helps us in making this kind of decisions, and because of all this it is tough to code and govern these projects. We will quickly see some terminologies before we go and understand the kernel trick. The table that you see here holds information about a person, the height, weight and IQ of a person, and a classification as to whether this person is adult or a child. Now this data is presented to a learning algorithm, and the learning algorithm learns the relationship of height, weight and IQ to whether a person is child or adult. Once this mapping is learned, if the data of a new person is given to this algorithm, data of height, weight and IQ is given to this algorithm, then this algorithm will be able to classify this person as an adult or a child with a reasonable degree of accuracy. So this is what the learning algorithm does. Now, if you look at the height, weight and IQ columns alone, this represents the data of a particular person. Each row of this corresponds to data from a particular person. In this case, it is height, weight and IQ. Now, we can take n such people's data and formulate this as an n cross 3 matrix. Such a matrix is called as a design matrix, and it is often represented by a capital X symbol. Now the last column, which says whether a person is adult or not, the last column can be taken out as a vector and be called as label or a target vector. Since this problem that we are seeing here is a classification problem, this particular vector holds labels. If this is a regression problem, this particular vector would hold scalar numbers. In any case, we would call this particular column as a label or a target vector, and it is often represented by small y. In this slide, we will see what is a gram matrix. In the previous slide, we saw what is a design matrix. Now, a gram matrix is created by taking this design matrix and simply multiplying it by its transpose. So if your gram matrix is represented by a symbol X, you just take X and multiply that with a transpose of X so that you get a gram matrix. And gram matrices are fundamental unit of information which is used in pattern analysis algorithm. In the future slides, I'll explain this more, but for now, this information that gram matrix means X star X transpose should be your takeaway. In the example shown in this slide, you can see that we take a design matrix which is 3 cross 4, which means that there are 3 data points and each data point is 4-dimensional. So we take this 3 cross 4 design matrix and multiply it with its transpose, which is a 4 cross 3 matrix, resulting in a 3 cross 3 gram matrix. And by the nature of this formulation, the gram matrix is a symmetric matrix and it's a square matrix. It's a n cross n symmetric square matrix where n is the number of data points. Even if we replace the design matrix X with a high dimensional mapping phi of x, the resulting gram matrix from phi of x, which is nothing but phi of x multiplied by phi of x transpose, that gram matrix would have the same structure as the original gram matrix, which is nothing but an n cross n symmetric square matrix where n is the number of data points. So the structure of the gram matrix doesn't change. This has significance because the downstream modeling tasks that use this gram matrix will see no change. They will not know that we have changed the mapping of x to phi of x. They will be completely oblivious to the fact because they are working with the gram matrix and the gram matrix structure has not changed. You see that? So this is an important feature of the gram matrix which we'll be using down the line. Gram matrices are represented by a symbol G. Each entry in the gram matrix is created from the dot product of the corresponding vectors in the design matrix, as you can see in the slide. So the complexity of creation of gram matrix is of order n squared multiplied by d, where n is the number of data points and d is the dimensionality. As you can see, n plays a big role here. If you have millions of data points, then kernel methods are not for you. So basically, kernel methods do not scale well with the increase in number of data points. There are certain methods that are proposed in literature to alleviate this problem, but the fact remains that kernel methods do not scale well with the number of data points. Just keep that in mind. But the problem that we are addressing here is the problem with D. The D starts exploding when we start exploring second order, third order features. We have seen this before. So when the number of dimensions increase, then we have a real problem with the computational complexity of the gram matrix. And how kernel methods alleviate this complexity is what we are going to see now. So I spoke about gram matrix earlier. Let us dive deeper into it. Consider a pattern analysis algorithm which learns a linear function. The pattern analysis algorithm takes as input a design matrix X and a target variable Y. The design matrix is of the form n cross d, where n is the number of data points and d is the dimension of each one of your input data point. And the dimension of the label information is just an n cross 1 vector. It's a label specification for each and every data point, n data points. So it's an n cross 1 vector. And the pattern analysis algorithm learns a linear relationship between the design matrix and the label or the target. So if a new data point is given to this pattern analysis algorithm, it can make a prediction for y by doing a linear operation. Usually the pattern analysis algorithm learns a weight vector w from its design matrix and the label information. From x and y, it learns a weight vector called w. So when a new data point is presented to the algorithm, it just simply takes a dot product of the weight vector with a new data point and produces a prediction for y. This is how most of the pattern analysis algorithm which learn linear functions work. And it can be shown that the information bottleneck for such linear algorithms is coming from a special type of matrix called gram matrix, which is created by taking the design matrix X and multiplying it with its transpose. So the design matrix is an n cross d matrix. You multiply that with a d cross n matrix, producing an n cross n symmetric square matrix. Such a matrix is called as a gram matrix, and it can be proven that the information bottleneck of such linear pattern analysis algorithms is contained in the gram matrix. Down the line, I will take the example of linear regression. I will show how gram matrices play a central role in the solution for the linear regression problem. So coming back to gram matrices, if I replace this gram matrix X star X transpose with phi of X multiplied by phi of X transpose, where phi of X is a high dimensional mapping of X, the resulting gram matrix still has the same structure, which means that the downstream modeling task of the pattern analysis algorithm doesn't need to worry about whether we used X or whether we used phi of X to create the gram matrix. They can all seamlessly coexist with this change. So this feature promotes modularity. So this is point number 1. That is the first takeaway. And the second thing is we use phi of X instead of X so that we can build a linear classifier or a linear algorithm in higher dimensions, but it would actually correspond to a nonlinear decision boundary in lower dimensions. We have seen this before. So that is point number 2. Gram matrices have a very interesting property. Gram matrices arising from X into X transpose are always positive semi-definite. What is positive semi-definite? If a matrix G is positive semi-definite, then it means that for any vector V, the dot product of this vector with the transformed version of this vector created by multiplying G and V together is always positive. Or in other words, V transpose multiplied by G multiplied by V is always greater than or equal to 0. Matrices that have this property are called as positive semi-definite matrices. Now on the left hand side, I have given a proof that the gram matrix is always positive semi-definite. You can pause the video and watch the proof once. We can also prove the vice versa property, that is, a symmetric matrix which has PSD property can always be decomposed into X transpose. I queried perplexity.ai, which is a Gen AI tool, about it, and it reasoned it like this. It said that a PSD property, a symmetric matrix with PSD property, will have positive eigenvalue, and when we eigen decompose this matrix into something like Q into diagonal matrix into Q transpose, this diagonal matrix would have positive elements in the diagonal. So we can take a square root of that since it is positive, and then distribute between Q and Q transpose and make it look like some X into X transpose. That is how it is done, and that is how the Gen AI tool reasoned. I did not go and verify this, but I verified that this property is true, that Symmetric PSD matrix can always be decomposed into X transpose. And we already saw that if a gram matrix arises from X into X transpose, it is PSD. So the corollary is that if a matrix is not PSD, it can never be decomposed into X transpose. This property will come very handy as we analyze kernel functions and their behavior in downstream. So as promised, I'm going to take the linear regression problem and show the occurrence of gram matrix in the solution to the linear regression problem. But before I do that, I want to have a small prelude where I would explain what I will be trying to do so that you can follow the next slide better. Consider a linear analysis algorithm which has learned a decision boundary called 2x plus 3y. Just by looking at that equation, we can tell that the weight vector learned is 2, 3, and the algorithm was trained on a set of data points which were all two-dimensional. So that's the x and y. So the design matrix was an n cross 2 design matrix where there were n data points and each data point was a two-dimensional data point. Now what we will try to prove in the next slide is that such a 2, 3 is nothing but a linear combination of the input data points. So you have a design matrix X which has n data points. If we linearly combine this n two-dimensional points, we will be able to get this W. That is what we are trying to say, and that is called as a dual form, as you will see in the next slide. And this is what is represented in the screen as W is equal to X transpose star alpha. X is nothing but n cross 2, and when you transpose it, it becomes a 2 cross n matrix. Alpha is a linear combination of n points, right? N two-dimensional points. So it's a n cross 1 vector. So 2 cross n multiplied by n cross 1 will give you 2 cross 1. So that is your weight vector. Now we will try to prove that this alpha, which represents the linear combination of all input data points, this alpha is a function of g and y alone, where g is the gram matrix and y is the target or the label information. So an alpha is the intelligence learned from the system, correct? So to learn this intelligence, it's enough we provide the gram matrix and y. This is the point that we will be trying to make, and let's move to the next slide and see how this applies to linear regression. Let us take a look at linear regression. On the left hand side of the screen, you see the primal form where the weight vector is given by the expression X transpose multiplied by X whole inverse multiplied by X transpose multiplied by Y, where X is the design matrix. We have already seen this design matrix. It has got n data points, n rows. Each data point has d dimensions, so it's a n cross d matrix. And y is a vector of real numbers that we are trying to approximate. Once we get the value of w, if you multiply x with w, you will closely approximate y. That is the problem that linear regression is trying to solve. And once we have found out this weight vector w, if we get a new data point called x, to predict y, all we have to do is take a dot product of this new input x along with w, and then you get a scalar number which approximates the value of y for the new data point. That is how we predict. This is how linear regression works. Now we want to show that this w is a linear combination of training data points. The training data points are in the rows of x. So a linear combination of the rows can be given by X transpose into alpha. When you do a X transpose, each column becomes your training data point. When you multiply it with a vector, it represents a linear combination of columns. A matrix vector multiplication is nothing but a linear combination of the columns of the matrix. So we need to show that W is of the form X transpose into alpha. That's the first thing we want to prove. Then we'll prove this alpha is nothing but a function of the gram matrix and y alone, and it does not involve the individual coordinate of x, just the gram matrix and the y. This is what we want to prove. Let us focus on the dual form now. We start with the expression of w from the primal form, except that we replace the term x transpose into x whole power minus 1 with x transpose into x multiplied by x transpose into x whole power minus 2. So once we write it like this, it allows us to write w as x transpose multiplied by the terms in LO. The terms in LO becomes this vector alpha. you can just work out the matrix dimensions. You will know that that reduces to a vector alpha, n cross 1 vector alpha. So this proves our first point, that the weight vector can be written as a linear combination of the training data points. Now what is alpha? Alpha is the terms in yellow, which is nothing but x multiplied by x transpose into x whole power minus 2 multiplied by x transpose into y. And now we have to show that this is a function of gram matrix and y alone. At the outset, we don't see any gram matrix at all here, but if once you multiply this equation by x transpose into x multiplied by x transpose on both sides, you can see that it reduces to the form where we can say alpha is equal to inverse of G matrix multiplied by y, where G is the gram matrix. So this proves that alpha is a function of just the gram matrix and the y. I found this derivation in the URL that you see there from the Cornell University. It's a very good resource. You can check this out. And back to our problem now. Now we have proved that the W, the weight vector, is a linear combination of the training data points, and that linear combination alpha is just a function of G and y and does not involve any direct coordinate of the data points x. It's only the dot products and the y that matters. Now let us look at how predictions are made for a new data point, especially when the learning has happened in the higher dimension. So before we do that, let us first recap what we do in the lower dimension. On the left hand side, you see this equation, weight vector is equal to x transpose star alpha. This basically says that the weight vector is nothing but a linear combination of the training data points. This is the dual form. And this alpha, which is a linear combination, can be expressed as a function of the gram matrix arising from x and y, which is the target variable. Now when a new data point x comes in, we need to make a prediction for it. In the lower dimensional case, it's very straightforward. We take a dot product of the weight vector and the new data point x, and that gives you a scalar, and that becomes the prediction for the new data point x. Whereas in high dimension, we learn the weight vector as a linear combination of high dimensional data points. So which is represented as W is equal to phi of x transpose multiplied by alpha. And since we are taking a linear combination of high dimensional data points, the weight vector itself is a high dimensional data point. It's a high dimensional vector. And this linear combination alpha is a function of the gram matrix arising from phi of x and y, which is the target variable. For a new data point x, we cannot directly perform a dot product of the weight vector with x because weight vector is in higher dimension, x is in lower dimension. So we promote x to phi of x and make it a high dimensional point before we take the dot product with the weight vector. And the result of the dot product is the actual prediction. That is how prediction happens when we do high dimensional mapping. The reason why I talk about this now is because this can serve as a good baseline to compare with the predictions that we will make when kernel functions are in place. So far we have seen that in order to leverage nonlinearity, we take this low dimensional design matrix x and convert that to a high dimensional design matrix phi of x, and then we compute a gram matrix which involves significant amount of computation, and then we pass this gram matrix to the linear method. What if I tell you that I can take you from x to the gram matrix only using low dimensional calculations and without explicitly specifying any kind of high dimensional mapping? So that sounds like a steal, right? That is exactly what the kernel trick does. It takes the x, which is a lower dimensional design matrix, and passes it to a function called special function called as kernel function, which converts this lower dimensional design matrix to a gram matrix without performing any high dimensional mapping. However, the kernel functions are special, and so this gram matrix can be seen as arising from high dimensional spaces. So without specifying any high dimensional mapping, without performing any complex computations in high dimensions, we achieve the same effect using kernel functions, and that is why this is called as the kernel trick. We have already seen the importance of gram matrix in the context of linear methods. A gram matrix is created by multiplying the design matrix with the transpose of itself, x multiplied by x transpose. On the left hand side, you see this gram matrix Each entry g of I comma j in the gram matrix comes from the dot product of xi and xj, as you can see in the left hand side figure. Now when we use the kernel, we simply replace the dot product with a kernel function invocation with xi and xj. So the element in the gram matrix g I comma j will be k of xi comma xj. That is how we create a gram matrix from a kernel function. Also, as we saw in the previous slide, the gram matrix that arises from kernel retains a nonlinearity but without the computational cost involved in high dimensional mapping. So that's the advantage of the kernel method, or that is what is called as the kernel trick. In this slide, we see how to create a gram matrix using kernel functions. On the left hand side, we see a design matrix, which is a 3 cross 4 matrix. 3 data points, each data point is 4 dimensional. We name these data points as x1, x2 and x3. x1 corresponds to the first row, x2 corresponds to second, and x3 corresponds to third. To create a gram matrix from this design matrix, we need to create a 3 cross 3 matrix. And the I comma jth entry of this gram matrix Gij is created by calling the kernel function with xi and xj as argument. For example, we have highlighted a particular entry in the gram matrix on the right hand side matrix. You can see that we take the third row second element of the gram matrix, and then we show that we are creating that by invoking the kernel function with x3 and x2 as argument. What is x3? x3 is the third row in the descent matrix, which is a 4-dimensional vector, and it is 8, 21, 30 and 2. Similarly, x2 is also a 4-dimensional vector, which corresponds to the second row in the descent matrix, which is 6, 10, 12 and -1. By passing these two vectors to the kernel function, we create a scalar and we populate the 3, 2 entry of the gram matrix using that scalar. And this is how we populate the entire gram matrix. Now, since the kernel functions can be thought of arising from dot products from high dimensional spaces, we can think of the gram matrix to arise from some y star y transpose, where y is a high dimensional mapping of x. So that is the key point to note here. Now that we have seen how to create a gram matrix using kernel functions, let us look at how we will make predictions for a new data point with kernel functions. When we are manually specifying the high dimensional mapping, we have already seen how we will make predictions for a new data point. We simply find out the weight vector as a linear combination of the high dimensional data points which we have specified. So we can find out this weight vector, and then we take the dot product of this weight vector with the high dimensional mapping of the new input point, and we arrive at the prediction. Very simple. But that's not the case with kernel functions, because in kernel functions we only abstract out the dot product without specifying the high dimensional mapping. So in such a case, how will we perform the prediction for the new data point? That becomes a challenge, right? Ideally, how we should be doing the prediction is, we take a linear combination of these unknown high dimensional data points and find out this weight vector, and take a dot product of this weight vector with the unknown high dimensional mapping of the incoming point x. Now there are too many unknown stuff going on here. How do we do that? The idea is, do not try to compute w. Keep w as a linear combination of unknown data points and allow the dot product to come inside the linear combination. Since dot product distributes over addition, we can allow the dot product to come inside the linear combination, and once it comes inside, we can replace the dot product with a kernel function. That is exactly what you see here on the right side. One another distinct advantage that the kernel function brings is the ability to reason through the kernel function and its idea of similarity. As we have seen before, kernel functions are very similar to dot products. If you look at dot products, when the vectors are aligned, it gives you a big number. When the vectors are orthonormal, it just gives you 0. So a dot product is a measure of how similar two vectors are, right? In a very crude sense, we can say that. Similarly, kernel functions too take two vectors and returns a scalar, which can be seen as a similarity score. So depending on how the kernel function is constructed, you can easily reason about, oh, what would this kernel function consider as close data points or similar data points. What are the hyperparameters of this kernel should I tune so that this kernel becomes more amenable to my problem? or is this kernel even suitable for my problem? For example, if you have a descent matrix X and descent and a vector Y, if you know three or four points in your descent matrix which are similar because their Y values are similar, then you can go and reason about what will the kernel function say about these points. Now, can I tune the kernel function's hyperparameter to ensure that these similar points are actually regarded as similar by the kernel functions? You need to think through this and then decide wisely what is the kernel function that works for your particular problem. This is extremely important. Just because people think that, oh, I got this kernel, I just plug it in and then I'll see how it works. But instead of doing that, if you go about systematically reasoning about your problem and the suitability of the particular kernel for your problem, you will be in a much safer zone. That sounds too good to be true, right? So I think we should see an example. So what you see here is a n cross 2 matrix. On the left hand side you see this n cross 2 matrix, which is a low dimensional design matrix. And then we define a mapping in the first green box wherein we take a two-dimensional point, which is a row in the X matrix, and then we convert that to a three-dimensional point using the mapping specified in the box. Now you have got a three-dimensional representation, so this n cross 2 matrix can be converted to a n cross 3 matrix. Now dot products in this space, you can see in the second green box, the dot product in this new three-dimensional space can also be achieved by simply performing the dot product in lower dimensional space and simply squaring it. Squaring is just an extra multiplication operation, right? So we avoid the computational complexity. We don't have to specify the high dimensional mapping. We simply perform the square of the dot product in low dimensions and we achieve the same effect of specifying a high dimensional mapping and taking a dot product in high dimension. So this is a kernel, and what you see here is a kernel trick. Not only for n cross 2, we can also prove this for an n cross d matrix. If your design matrix is of the form n cross d, where each data point has d dimensions, simply take a dot product of any two chosen data points and then square it. The resultant expression can be seen as coming from a dot product from a higher dimensional space. You can work this out yourself. You can just follow the same example as the previous one where we did for n cross 2. You can do the same thing and you should be able to prove this easily for an n cross d case as well. And that is left as an exercise to you. We can also demonstrate a more advanced example. For example, in the link that you see on the screen, the professor explains how an RBF kernel can be expressed as dot product of two infinite dimensional vectors. I highly recommend you watch this video. It's a very short and crisp video and you'll simply be amazed at how easily the professor breaks it down. Now we have sufficient background to understand the topic of today's talk. So going forward, we will see what are kernel functions, what are the special properties they need to possess in order to qualify as a kernel function, and then we'll also prove that kernel functions are equivalent to dot products arising from higher dimensional spaces. Much of what I'm going to talk about today comes from this book called Kernel Methods for Pattern Analysis by Mr. Christianini and Mr. Taylor. It's a very sophisticated book and hence somewhat costly. So if you decide to know more about kernel functions, this is the book you have to go after, and this is available in Amazon. You can buy it and read it. Several questions arise at this point. Do gram matrices arising from kernel functions have PSD property? What kind of functions qualify as kernel functions? Can all functions qualify? So what are the qualifications of a kernel function? And what is the high dimensional mapping behind these kernel functions? The simple answer to the first question is yes, gram matrices arising from kernel functions have to have the PSD property, because if they do not, then they cannot be expressed as A into A transpose. Then we cannot claim that, oh, gram matrices arising from kernel can be thought of some X into X transpose where X is some high dimensional matrix. We cannot claim that, right? So they have to satisfy this property. The second important and the most interesting question is, what is the high dimensional mapping behind this kernel function? So that we are going to see down the line. Not all functions can be kernel functions. A function has to satisfy certain properties to qualify as a kernel function. The first and foremost is that it needs to look like a dot product. The function signature should match the function signature of a dot product. And what is the function signature of a dot product? It accepts two vectors of same dimensionality and returns a scalar. So a kernel function should match this function signature. That is the first requirement. The second requirement is that a kernel function has to be commutative, just like dot product. So if you have k of x1, x2, if I flip the argument and make it k of x2, x1, it should both of them should return the same result. So that is, the kernel function has to be commutative. Third, if I form a kernel matrix from any subset of the R power n space, then such a kernel matrix has to be positive semi-definite, PSD. So that has to satisfy. For example, if I go to R power n space, which is the space of n-dimensional vectors, I pick some 150 data points out of that, and then I create a 150 cross 150 matrix using k of xi, xj, and then if I form this kernel matrix, such a matrix has to be positive semi-definite. Now I can pick 150 points, I can pick 50 points, I can pick 100 points, I can pick 5 points. For any number of points that I pick, for any subset that I pick, it should create a positive semi-definite matrix. Otherwise, it cannot be a kernel function. Let's say there exists a function that satisfies all these three properties, and naturally it is a kernel function. And we want to prove that such a kernel function is equivalent to a dot product arising from a higher dimensional equivalent of its input. For example, k of xi, xj, we want to show that it is equivalent to a dot product of phi of xi and phi of xj, where phi is a mapping from R power n to a high dimensional space. Note that we are providing this proof generically for all functions that satisfies these three properties. So we are not talking about specific kernel functions here. We are not giving proof for RBF or exponential sine squared or polynomial like that. No, we are not doing that. We are doing it at a very abstract level for all functions that satisfy these three properties. So expect that the proof will also be at a very abstract level. And how are we going to prove this for all the kernel functions? We will do that by first constructing our own Hilbert space. A Hilbert space is something like the 3D space that we live in. We create a new space, and then for every element in R power n, the n-dimensional real vector space, we provide a mapping, equivalent mapping to an element in our space, our new space, and then we'll hypothesize that dot products in our space creates the kernel function, and the entire setup would work only if all the three properties are satisfied. Even if one of the properties is not satisfied, then this will break down. This entire setup would break down. So that is exactly how we'll prove this for all kernel functions. Let us take a deeper look into what space means. Let us first take the example of the three-dimensional space that we live in. Our space is defined by three directions, x, y, and z, or z. The unit vectors in these three directions form the basis of our entire 3D space, which means that any vector in three-dimensional space can be written as a linear combination of these three unit vectors, right? Similarly, if we want to define a space, the first thing we need to define is what are the basis vectors of our space. Once we define the basis vectors, we need to come to a state where we can define a linear combination. To define a linear combination, you need to define scaling by a multiplication by a scalar and addition of vectors. Once we define these two, we can then perform linear combination of these unit vectors or the basis vectors. Then we need to prove that these linear combinations are closed, which means that these operations create elements which are present only within our space. Then we need to satisfy other properties like scalar multiplication distributes over vector addition, and there is a set of axioms that you need to satisfy in order to qualify as a space. So we need to do all that and ensure that our space is very similar to an R power n space. Once we have that, then we can go and do the rest, like defining the mapping, talking about the dot products and the equivalence to the kernel function, and the contingency of the properties, all that we can talk. But to define the space, we need to first do the basis vectors and ensure that the basic axioms of being a space is satisfied. Now, if you're a mathematician interested in knowing more about this concept, your Google search term is functional analysis. Go read on functional analysis. It's a very abstract subject, very tough subject. But if you are a Puritan who is interested in it, please go and Google search for functional analysis. As illustrated in this diagram, we will first create the new space, that one that you see on your right, and then we'll provide a mapping for each and every point in R power n space to the new space. And this mapping is 1 to 1. This is the first thing that we will do, and then we'll hypothesize that the dot products in the new space is same as running kernel functions on the R power n space. This is a hypothesis, and then we'll go ahead and prove that such a dot product can be constructed only if the kernel function satisfies those three properties, which is nothing but the kernel function returns a scalar, the kernel functions are commutative, and a gram matrix formed from the kernel function automatically satisfies the PSD property, positive semi-definite property. And the reason, the way we will do this is because dot product in spaces are supposed to have certain properties. And when we go ahead and enforce these properties in the new space, we will automatically discover that the kernel functions have to satisfy these three properties. If not, we cannot construct a new space. So this is how we will prove that for every kernel function that satisfies these properties, there exists, we can create a new space and hypothesize that dot products in this space results in kernel functions. So this is how we will go ahead and prove what we want to prove. Before we go and create a space for ourselves, let us first review the concept of vector spaces. This would mean understanding the requirements to satisfy in order to qualify as a vector space. This would mean understanding the properties that need to be satisfied for a norm function. This would mean understanding the requirements that need to be satisfied by the inner product function. So let's go and review all this before we go and create this space for ourselves. A vector space is defined as a set of elements referred to as vectors. These elements can be added together and they are closed under addition. That is, if you choose any two elements and add them, it should produce an element that is present in the set, not outside the set, right? The second property is that we should be able to multiply these vectors using a scalar, and such multiplications should result in an element that is present in the set. That is, it has to be closed under multiplication by scalars. Apart from these two fundamental properties, a set of other properties also need to be satisfied. Vector addition has to be associative. Vector addition has to be commutative. We need to have an identity element for vector addition. If we have an identity element, then we need to have an inverse element as well, correct? Then there are also properties related to scalar multiplications and distributivity. You can pause the video and check these axioms. Only if a space satisfies all these properties, it can qualify as a vector space. Vector spaces are characterized by basis vectors. We have seen about this just a few moments back. The important takeaway is that if we define the space as a span of basis vectors, then automatically such a space will be closed under vector addition as well as scalar multiplication. So that is the biggest takeaway. So instead of defining a space and then coming up with a basis vector, you create the basis vectors and tell that the space is a span of the basis vectors, then automatically you are closed under vector addition and scalar multiplication. A vector space over reals is an inner product space if there exists a function that takes two arguments, two vectors as input, and returns a real value. The function has to be symmetric, that is, it's commutative, and the function has to be bilinear, that is, linear in both its arguments, and it should satisfy that if the map is invoked with the same vector in both the arguments, it should never return a negative number. It should always be greater than or equal to 0. If it satisfies all these properties, all these four properties, then such a map is called as an inner product. and the space is said to be an inner product space. So time to define our own space. One thing that we need to keep in mind is that we are creating this space, so we are at the liberty to specify what are the elements of this space, what are the basis vectors of this space, how an addition would look like in this space, how a scalar multiplication would look like, how an inner product would look like. Everything can be determined by us. So just keep that in mind and let's proceed. It's now time to define the basis of our space. If you take 3D space, the bases are the three mutually perpendicular directions. So it is easy to grasp. In our case, the basis of our space will be functions. So what type of functions? We will take the kernel function, which takes two n-dimensional vectors as its input, and then we will freeze the first argument to be a specific n-dimensional vector. Now this will effectively convert the kernel function into a function that accepts only one argument, one n-dimensional vector as argument. We can define such functions for every n-dimensional vector in R power n space. Now each such function that we create will become a dimension in our space. So effectively our space becomes an infinite dimensional space. If you look at the screen, the third bullet point, you can see that I am using this notation k of xi comma dot to represent a function whose first argument is frozen to be xi and only the second argument is allowed to change. Such functions form the basis of our space. There are infinite such functions because there are infinite such xi's, and so there are infinite such bases for our space. And now a vector in our space looks like it's just an infinite set of numbers. That's all. The numbers are values of these dimensions. They are not dimensions themselves. The dimensions are the functions, but the value of the taken by the dimension can be real number. You need to make this distinction so that you understand what we are trying to build. Now that we define basis of our space, we now define basis vectors of our space. So as you see in the figure and as we discussed before, a vector looks like a normal vector, just that in case of unit vector, the particular dimension for which the unit vector stands for, that dimension alone carries a value of 1 and the rest all dimensions carry a value of 0. So likewise we will have infinite such basis vectors, but if we are defining our space from a limited set of n-dimensional vectors in the R power n space, then the number of basis vectors that we will have will also be limited by that. Now that we have defined basis vectors, our new space is nothing but linear combination of these basis vectors. So before we go and talk about linear combination, we need to understand what is scalar multiplication, what is addition, right? Only if we define these two properties, we can go ahead and say what does it mean to linearly combine functions, because each one of our basis vector represents a function, right? So when we linearly combine functions, what does it create? Does it create another function? If so, what is the semantics of that function? All that needs to be specified clearly before we can accept what a linear combination of function actually means. Now that we define basis vectors, it's time for us to define what addition looks like in our space. If you look at the expression on the left, we are trying to add two basis vectors. One corresponds to k x1 and another corresponds to k of x2. Now k of x1 is a function and k of x2 is a function. So we have to define what addition of functions represent in our space. So let's shift our attention to the right hand side. So let's call this addition as f and call that f is a function. So we are adding two functions, k of x1 and k of x2, and let's say that the resultant is a function called f. So if that's a function, then what is f of x? We have to define f of x, right? So f of x we need to define, and we have the privilege to define it in the way that we like because it is our space. And we will not do any complication, we will just do the natural stuff. So k of x1 plus k of x2 of x is nothing but k of x1 of x plus k of x2 of x. We just invoke these individual functions and add the result. the result is a scalar, right? So we will define addition like this in our space, and there are certain benefits of defining addition like this. We will see it in the next slide. We can extend this definition of addition to any vector in our space, because we are the ones who are defining addition. So for any vector in our space, we can say f plus g of x is nothing but f of x plus g of x. The benefit of this definition is that the addition of functions is now commutative as well as associative. I have given an example here. I have taken a function which adds x1, k of x1, k of x2 and k of x3, and we call it as h, and then we define two different ways of looking at addition. One is a left associative way and another is a right associative way, and in both cases it results in the same function. So we can say that regardless of whether we associate addition on the left side or the right side, it always gives us the same result, and this is an extremely important property that we have now achieved just by the virtue of defining addition in our function spaces. I would recommend you to pause the video and go through this step. It's not that hard. You should be able to see it very clearly. Now that we saw addition, let us shift our attention to scalar multiplication in our vector space. So the expression that you see on the left, it says phi star vector in our space. What does that represent? We will first say that this represents a function, because the basis vector 1 0 0 represents k of x1. So effectively what we are doing is phi star k of x1. This is what we are trying to do, and let us say that this is a function. Now since we define it as a function, we need to specify what does that function do. What is f of x, or in other words, what is phi star k of x1 of x mean? What does that mean, right? So now we will not complicate it. We will just say phi star k of x1 of x is the same as phi star k of x1 of x, right? You can see the green and the pink one. You might see this is kind of silly, but the important point that will help you understand this is the star operator that is on the green side of the expression is an operator in our space, whereas the star operator in the pink section is an operator in the real space, because when the function k is invoked with k of x1 as well as x with a second argument, it returns a scalar. So that's a scalar multiplication that is in a totally different space, right? Having this clarity will help you appreciate this concept much better. Now that we have tied the multiplication in the function space to the multiplication in real space, somehow we can enjoy the associativity and the commutativity that comes along with the real operator, correct? Just as in the case of addition. I'm not going to go into the details, but if you want, you can work this out. It's fairly simple to do. Another big advantage of defining multiplication in our function space like this is that it connects to the addition in function spaces, just like how multiplication connects to addition in the real space. So which means that phi star k of x1 is indeed k of x1 plus k of x1 plus k of x1 phi number of times. You can simply work this out, because on the right hand side we have got an addition expression, and addition is associative. We have seen that. So if you invoke this function with x, it simply means k of x1 of x plus k of x1 of x phi number of times, which is nothing but phi into k of x1 of x in real space, correct? The same, so that matches the phi star k of x1 definition as well. So this way the multiplication and addition in our function space are connected in the same way as multiplication and addition are connected in the real space. To conclude, the definition of scalar multiplication that you saw here, it's not necessarily applicable only for a basis function. It can be the same for any other vector, because we are the masters of our space and we define scalar multiplication thus. So the scalar multiplication can be extended to any general vector too. So the question is, does scaling distribute over addition in our space? So the expression that you see here, this is what we want to answer, and by just following the definitions we have seen so far, we can see that this can be easily proved for the example given here. And the same applies even if the vectors are non-basis vectors, which means that there are some generic vectors which are linear combination of the basis vectors. Even if they have generic vectors here, we can still prove that scaling distributes over vector addition in our space. So far we have been looking at basis vectors, addition of basis vectors, scaling of basis vectors. Now let us actually go and look at a normal vector. Consider the vector on the left side of the screen which says 12, 3, minus 10 all the way until 6. Now what it actually represents is 12 times the basis vector for x1 plus 3 times the basis vector for x2 minus 10 times the basis vector for x3 and so on, 6 times the basis vector for xl, where L is the last dimension, right? So that is what it represents, and we know that in function terms this can be written as f is equal to 12 star k of x1 plus 3 star k of x2 minus 10 star k of x3 all the way until 6 star k of xl. Now this we call as a function, but if we call this as a function we have to specify what is f of x. Now we know that addition in our space is associative, and we have also figured out what is a scalar multiplication of basis vectors in our space. Using both these definitions, we can just say that f of x is nothing but 12 star k of x1 of x plus 3 star k of x2 of x and so on. Again, the star and plus in the pink section is in real space, whereas the star and plus in the green section are operators in our space, the function space. Now keep that clarity in mind always. Now by the virtue of our definitions, we can simply represent a vector as a linear combination of the basis functions. And we have also given the semantics, what that function represents. We have also given the semantics. Now we will define our space as the span of our basis vectors. Just like how in the 3D space, we just say the 3D space is a span of the unit vectors along x, y and z or z directions. Similarly, we will say that our space is the span of our basis vectors. Similarly, we can prove that we satisfy all the axioms listed in this space, and hence our space qualifies as a vector space. So now it's time to define inner product, but before we do so for our space, let us first review the inner product in real vector space. Let's say you have two vectors alpha and beta, like the ones you see on the screen, and then you do a dot product. We all know that the dot product result is a scalar, and it is written by alpha 1 beta 1 plus alpha 2 beta 2 all the way until alpha l beta l. Basically we take the coefficients of a dimension and multiply them together, and then we add them up. But a dot product distributes over addition. So the question is, why are we not seeing the terms like alpha 1 beta 2, alpha 1 beta 3? Why are we not seeing this? That's the question that we need to answer. To know why we don't see terms like alpha 1 and beta 2, let us zoom in on that particular term in the dot product expansion. So if you look at this term, this evaluates to alpha 1 multiplied by beta 2 multiplied by the dot product of two basis vectors, and these two basis vectors are different. And in real vector space, the basis vectors are orthonormal, which means that by definition their dot products evaluates to 0 unless and until they are the same vector, same basis vector. Now what you see here is two different basis vectors, and hence their dot product will evaluate to 0, and that is the reason why we don't see terms like this in the dot product in real vector space. Now the question is, to qualify as a vector space, do you need to have an orthonormal basis? The answer is no, which means that in our function space, when we talk about dot products, the first thing we need to address is what is a dot product among the basis vectors. Should we define a value for it, or should we say they are orthonormal? Let us see it in the next slide. Our space will have non-orthogonal bases, which means that we define the dot product for basis vectors that are different, and we define a proper value for it. And this is how we define. If you see the screen, we take k of x1 and then we do a dot product with k of x2, and the result is nothing but a scalar, which is k of x1 comma x2. Being a scalar is one of the requirements for a dot product function, so we satisfy that. Now we have to check whether we satisfy the other properties of the dot product. Another property of dot product that we satisfy with this definition is the commutative property. Since k of x1 comma x2 is same as k of x2 comma x1, so the dot product of k of x2 with k of x1 will also be equal to the dot product of k of x1 with k of x2. So this means that we satisfy the commutative property of the dot product as well, and this is by the virtue of the kernel function being commutative. By the virtue of the definition we have adopted for the dot product, if we take any vector in our space which is represented by a function f, And then if you take a dot product of that with the basis vector, let's say the basis vector anchored on x2, then the resultant scalar is nothing but f of x2. So this is what is called as the reproducing kernel property. One can easily see how this works. You just take the alpha vector that you see on the left and break it down as alpha 1 multiplied by the basis vector for x1 all the way until alpha l multiplied by the basis vector for xl. You take it as an additive expression and then you do a dot product with the basis vector for x2, and since dot product distributes over addition, so every individual term of this additive expression will have a dot product with the basis vector for x2, and the resultant expression is nothing but the green box that you see on the screen here, and that is nothing but f of x2. Inner product functions need to satisfy an important property that they have to be bilinear, which means that they have to be linear in both of its arguments. One way to prove that a function is bilinear is to fix one of its arguments and then prove that it is linear on the other. This is exactly what we'll prove. You can see two boxes on your screen here. On the left hand side, we'll prove that we fix v2 and then we'll prove that the dot product function is linear on v1. And on the right hand side, we fix v1 and then we'll prove that the dot product function is linear in v2. So on the left hand side, we just write down the inner product as an inner product between the two summations, that each summation represents a vector. Now since dot product distributes over addition, what you can rewrite this expression as, you take alpha 1 k x1 and then you multiply that, or not multiply, but take a dot product of that with each term of the right hand side expression, which is in beta. Right? So the entire expression can be rewritten as sigma I is equal to 1 to L alpha I star. You take the k of xi inside each term in a beta vector and then you convert that into a k of xi comma xj. Right? Essentially this will come down to the last step. What you see is that the resultant expression for the dot product is sigma I is equal to 1 to L alpha I star v2 of xi. Now if I fix v2, xi is nothing but the basis vectors, right? So v2 of xi is fixed. So it's nothing but it's just a real numbers, right? Now if that is fixed, then it's nothing but a linear combination of alpha I, and we know that linear combination is a linear function anyway, right? So this way it's linear on alpha vector. Similarly, on the right hand side, we can apply similar logic, and we can see that if we make v1 as fixed vector, then it is linear on v2. So this proves that the dot product function that we have adopted is indeed a bilinear function. So this leaves us with our last condition, that the inner product of a vector with itself cannot be negative. That is, it has to be greater than or equal to 0. We take an alpha vector and write it out as a summation form, and then we take a dot product of these two summations, and since dot product distributes over addition, we rearrange the terms to get the last expression that you see there, which is nothing but alpha transpose multiplied by k multiplied by alpha, where alpha is your vector and k is nothing but a matrix formed by the dot product of every basis vector with every other basis vector. This is a symmetric matrix and a L cross L matrix, where L is the number of dimensions. And now this expression can be greater than or equal to 0 only if K is a positive semi-definite matrix, because this is exactly the definition of a positive semi-definite matrix. If a matrix K is positive semi-definite, then alpha transpose multiplied by K multiplied by alpha has to be greater than or equal to 0, and K has to be a symmetric matrix, correct? So we already proved all this. So if the kernel function satisfies the PSD property, then technically we can create a space where the dot products in that space create the kernel function. This is exactly what we wanted to prove, correct? That a kernel function arises from dot product from some space. So we have created an abstract space and then proved that dot product in that space is actually creating the kernel function. And if the kernel function satisfies these properties that we see here, then it's technically possible to create another vector space and show that dot products in that space create this kernel function. That's it. Now I just want to refresh your memory. So we talked about gram matrix and its importance to machine learning algorithms. The gram matrix is nothing but a design matrix X multiplied by its own transpose. It is a symmetric matrix. It is a n cross n matrix, and we know that every element of the gram matrix comes from a dot product of the participating vectors xi and xj. And we also knew that if I replace xi and xj with a higher dimensional representation, then we are able to learn nonlinear decision surfaces. So in that case, we replace xi and xj with phi of xi and phi of xj, and the gram matrix remains the same, and in dimensions it's still an n cross n matrix, but its individual elements now come from dot product of phi of xi and phi of xj instead of coming from xi and xj. And now the kernel functions, we proved that the kernel function can come from a dot product from a higher dimensional space. We already proved this. So this means that I can replace this phi of xi and phi of xj dot product in the gram matrix with simple kernel function invocation on xi and xj. So without doing an explicit high dimensional mapping of xi and xj, I just replace them with kernel function of xi and xj, which can be thought of as a dot product arising from a high dimensional space, and thus we avoid the computational complexity involved in mapping the individual vectors to high dimensions and performing dot product in high dimensional spaces. All that complexity is totally erased, and we now compute the dot product as just a kernel function invoked with xi and xj. So this avoids a lot of computational complexity, and that is why it is called as a trick, the kernel trick. I know this is a long video, so if you're still confused or if you've forgotten the gram matrix, just go over the earlier sections and you will know what it is, and you should be able to connect this together so that you get a full picture in your mind. So we have shown that if a function satisfies some properties like taking two arguments, vector arguments, and returning a scalar, and being commutative on its two arguments, and being a PSD function, then such a function qualifies as a kernel function, in that such a function can be represented as arising from dot products from a high dimensional space. So such a function can be used to replace the dot products in a gram matrix, and thus enables us to learn nonlinear decision surfaces in machine learning algorithms. There are other properties for a vector space like separability, completeness, and all that. If you want to go ahead and prove such properties for the space that we constructed, feel free to do that. The Google search term for this is functional analysis. This is the area that talks about all these things. It's pretty abstract and tough, but if you're interested, please go ahead and research it for yourself. So after doing all this, I kind of understood what a kernel function is and the relationship of the kernel function with the dot product, what makes it special and all that. But the question that lingers in me is that who determined the rules of a dot product? How did they even arrive at these rules? Why were these rules made? What was the motivation? Who designed these rules? I have no answer to all these questions, but if you know some of these answers, please leave a comment in this video or make another video and explain it to the community. It will be very useful. Thank you. So that's all, folks. We have come to the end of this video. If you like the video, if it really helped you, please leave a comment, like, and subscribe to my channel. And thank you for watching this. Have a good day.